going to start our video lectures on section 4.3, which is about how derivatives affect the shape of a graph. And I need to start by giving us a couple of definitions. The definitions are actually stated in section 1.1 of your text, and we're just referring back to them in section 4.3. But it's the definition of what it means for a function to be increasing, and then I'm also going to tell you what it means for a function to be decreasing. Okay. So the definition says that f of x is increasing on an interval I if for all x1 and x2 in the interval, so if I pick a pair of x values in the interval, if x1 is smaller than x2, then f of x1 is smaller than f of x2. Okay. So here's an example. E to the x is a function that's always increasing, and we can see that by inspection. So what does this definition tell us? Well, I could take as my interval the entire real number line from negative infinity to infinity. Note that this definition doesn't state whether it's an open or closed interval, so it applies to both. Okay. So if I take the two fingers, my two index fingers, and I put my left finger down and my right finger down on the graph, okay, this point is to the left of this point. It's also lower down than this point. My function is increasing. Okay. So basically, if it's increasing, points to the right are going to be higher up. But there's an interesting technicality with this, because if I look at y equals x squared, I can definitely see that f is decreasing here. We'll define decreasing in a moment, and increasing over here. But if I wanted to define the interval where f is increasing, and I'm just going to use an up arrow to abbreviate that, it's actually the interval from 0 to infinity, and that's a closed bracket there. 0 is included in that interval. And that's a little bit counterintuitive, because I want to look at that and say, but wait, f isn't increasing at 0. And you're right, it's not. 0 is the location where f stops decreasing and starts increasing. But the definition of increasing is not a definition that pertains to an individual point. The definition of increasing talks about an interval, which is about how I would compare a point in that interval to another point in that interval. And if I chose 0 as one point in my interval, and any point to the right of 0 as my other point, the point to the right would be higher. So this criterion is satisfied on the interval including 0. So this is a definition about increasing on an interval, talking about how we compare the values of the points, rather than a definition about increasing at a point. I would sort of argue that at this point, the function is actively increasing, because as we pass through that point, we're moving up. Here, the function is not actively increasing as it passes through that point, but yet I include it in the interval over which I say things are increasing. The definition for decreasing is very similar. If I wanted to change this to decreasing, I would simply make a change in my inequality. I don't want to change both inequalities, because right now I'm saying the point on the left has the lower y value. If I changed both inequalities, I'd say the point on the right has the bigger y value, which is equivalent. But now I'm saying the point on the left has to have the bigger y value. Now, I can see that's going to be true on the left half of this parabola. So I would say f is decreasing on the interval from negative infinity to 0. 0 gets included in that one too. We can include these finite endpoints as long as this comparative definition is satisfied. Okay, so that's our definition. What does that have to do with calculus? Well, when we've taken derivatives, we know that derivatives are slopes of tangent lines, and we've been using the fact that we're going to get a positive slope if the function is going up, and a negative slope if the function is going down. So, we can say if f prime of x is bigger than 0, meaning it's positive, on an interval I, then f is increasing on that interval I. And again, it does not matter whether that's an open interval or a closed interval. But there is one fine detail that your book doesn't really mention a whole lot, but I think it's important, so I'm going to throw it in. If f prime of x is bigger than 0 on an open interval that doesn't include the endpoints, and f is continuous on the closed interval that does include the endpoints, then I can say f is actually increasing on the closed interval from a to b. I get to throw in those finite endpoints. Let's just take a look at this. And let me give you the second part of this, and then we'll take a look at it in relationship to x squared. Okay, so this also says that if f prime of x is less than 0 on an interval, then f is decreasing on that interval. And this additional statement also applies for decreasing. So if f prime of x is negative on AB, the open interval, and f is continuous on the interval including the endpoints, then we can say f is decreasing on that closed interval. Okay, so let's just take a look at how this relationship between the behavior of f and the sign of f prime plays out with a function that we're very, very familiar with. So if I look at f of x equals x squared, my beautiful and lovely parabola. Okay. If I take a look at f prime of x, that's going to be 2x. Okay. So I'm going to use this. I'm going to pretend I don't know that the graph looks like this so that I can see where it's decreasing and where it's increasing. If I wanted to figure that out from the derivative, I would say, okay, I need to know where this thing is positive, and I need to know where it's negative. So I'm going to draw myself a number line, and I'm going to start by marking off any critical numbers. Critical numbers, remember, are places where the derivative is either 0 or undefined, but that means critical numbers are places where the derivative could change sign. Because the only way to change from positive to negative or from negative to positive is to either jump over 0 or pass through 0. So that would mean that the derivative would have to be either 0 or undefined. Now, this is always defined. And of course, 2x equals 0 if x equals 0. So my only critical number is at 0. Now, what that tells me is that my function, the derivative function, has a consistent sign on this entire interval. Because if this is the only place it can change sign, it doesn't change sign anywhere over here. Same thing here. We're going to have a consistent sign over here. So what I'm going to do is just pick a test number. I'm going to pick -1. Usually when I'm picking a test number, I like to write that test number a little bit lower down, and I also put it in parentheses. That's giving myself 2 visual cues that that's not a critical number that I'm marking off as a possible place where it could change. That's just a number that I'm plugging in to check the sign of things. So I can say at -1, 2x would be negative. Okay. Number to the right of 0, I think I'll plug in 1. Okay. So then 2x would be positive. Excellent. And the theorem tells me that that means that my function is decreasing on that interval and increasing on this interval. Notice just by drawing in these arrows, that kind of gives me a sense of the shape of the graph. This is going to become really useful when we're trying to sketch graphs that we don't know ahead of time what they look like. All right, so that's great. And my function is continuous. If I look at the original function, it's continuous at 0, so that means I can throw in that finite endpoint. So I would say f is increasing on the interval from 0 to infinity and decreasing on the interval from -infinity to 0. Again, the fact that 0 gets included in both does not mean that I'm saying the function is both increasing and decreasing there. Here I'm saying if I compare 0 to a point to the rightmost point will be bigger. Here I'm saying if I compare the value at 0 to a point on the leftmost point will be bigger. Okay, so again, the definition of increasing and decreasing is a comparative one. But by looking at the sign of the derivative, we can determine the intervals over which a function is increasing and decreasing. So let's try an example of that. Let's let f of x equal x squared e to the x. And I want you to find the intervals on which f is increasing and decreasing. And I do want you, if possible, to throw in the finite endpoints. So you're going to start by finding the intervals where f prime is positive and negative, and then if the function is continuous at the places where the sign changes, you can throw in those endpoints. Again, the book really glosses over that, so you'll notice that in the homework, I've actually given correct solutions that include the finite endpoints for some of the problems. So as you're doing the homework problems for this particular section, 4.3, do make sure that you're looking at the assigned list when you're checking your answers for those intervals, because the book just always does open intervals, and that's actually not right. So, okay, so I'm going to have you try this problem on your own, and then in the next video, we'll take a look at it together.